The final part of the plan was simple to describe and unforgiving to execute. The atmosphere and parachute would remove most of the speed. This lander may have touched down early, not on Mars, inside its own flight software. Investigators found a false signal from the landing legs could survive until the engines armed for touchdown. That happened about 40 meters up, where shutting down would turn descent into an unsurvivable fall. But no flight data proves it. So why did NASA think this was the most likely answer? Mars Polar Lander reached Mars on the 3rd of December 1999. It had been built to descend near the planet's south polar region, deploy a robotic arm, and begin a surface science mission. Before entry, the lander sent its final cruise telemetry. Then, the signal stopped as planned. The spacecraft would cross the atmosphere, deploy its parachute and legs, ignite its descent engines, and land without talking to Earth. Only afterward was it supposed to transmit the engineering data stored during descent. That meant the silence was not initially evidence of failure. The first expected message from the surface was supposed to carry the story of what had just happened. It never arrived. Repeated attempts to establish contact found no lander and no final record of the descent. Investigators had to reconstruct the missing minutes from design documents, software logic, and tests on Earth. The lander would separate, fire its descent engines, and use radar and inertial sensors to control the approach. Each landing leg carried a magnetic touchdown sensor. When a footpad contacted Mars, it would signal the software to stop the engines. That shutdown had to happen quickly. If the engines kept pushing after one foot touched, the thrust could tip the lander. So a valid touchdown indication demanded immediate action. But the touchdown sensors had another behavior. When the folded legs opened earlier in the descent, their movement could produce a momentary signal that looked like contact. It was a mechanical transient, not a footpad touching Mars. Safety now depended on when that indication counted and what happened to one that arrived too early. The board's most probable sequence began with that deployment pulse. Flight and development testing showed that leg deployment could generate a false indication in a Hall effect touchdown sensor. The software would accept a signal as a valid event if it remained present for 2 consecutive readings. Most of the observed deployment transients lasted long enough to satisfy that rule. With 3 landing legs, the board judged it almost certain that at least one sensor would produce an indication the software accepted. That still was not enough to stop the engines. The touchdown logic was not supposed to act while the lander was high above Mars. The intended protection was to ignore indications before the logic was enabled, but the implementation did not properly discard the early event. It could record and retain it. The pulse itself was momentary. The software state it created could persist. The dangerous event may have begun when the legs opened, then waited for another part of the landing sequence to give it authority. That authority arrived at about 40 meters above the surface. At that altitude, the touchdown sensing logic became active. In the board's reconstruction, the software would examine the state it had retained from leg deployment, accept that state as touchdown, and command the descent engines to terminate thrust. Nothing in that sequence required a new sensor pulse at 40 meters. The false indication could already be waiting. This is why the lander thought it had landed is useful only as shorthand. It did not make a human-style judgment. A transient, satisfied, and acceptance rule. The implementation preserved the result. A later gate made that result actionable. In the correct situation, fast cutoff was a safety behavior. The failure, if the board was right, came from applying that valid response to an invalid state at the wrong time. A mechanism designed to protect the lander during real touchdown may have removed the only force keeping it airborne, and 40 meters did not leave enough room for recovery. The board reported that the lander would have been descending at about 13 meters per second when touchdown sensing enabled. With the engines off, Mars's gravity would continue accelerating it. The estimated speed at the surface was about 22 meters per second, roughly 9 times the nominal touchdown speed of 2.4. The investigation concluded that the lander could not have survived an impact at that estimated velocity. Those numbers are not measurements transmitted from the spacecraft. They belong to the board's probable sequence. No recovered telemetry shows the engines turning off, the fall, or the impact. They establish consequence. If the retained indication triggered shutdown at 40 meters, this was not a rough landing the spacecraft might ride out. That distinction is the reason the official report called premature engine shutdown the most probable cause, not the confirmed cause. The review board evaluated 7 plausible Mars polar lander failure modes. Premature engine shutdown stood out because evidence from the landing leg tests and the software design formed a specific chain. A known transient could satisfy the acceptance rule. The implementation could retain it. The logic enabled at 40 meters. The calculated result was unsurvivable. But there was no corroborating flight data. The spacecraft had not transmitted its final descent, and the stored record never reached Earth. So 6 other possibilities could not be ruled out. That does not make every branch equally likely. It means the strongest reconstruction never crossed from compelling inference to observed event. The evidence that made the shutdown sequence persuasive came largely from Earth. And the same Earth testing also revealed why the defect had survived. Touchdown sensing was tested. Landing leg deployment was tested. Flight software was tested. But the board found that touchdown sensing had not been tested in the lander flight configuration. That difference matters. A component test can show what a sensor does. A software test can show how logic responds to selected inputs. The mission needed a configuration joining the real sensor behavior, deployment timing, flight software, and transition into the enabled state. Each piece could appear acceptable, while the interaction remained dangerous. The transient was not, by itself, a broken sensor. The quick cutoff was not irrational logic. The enable point was not a failure. The retained state connected them. An end-to-end test in the flight configuration should have asked whether a deployment signal accepted earlier could still exist when touchdown sensing became active. That exposure did not occur, and the error remained undiscovered. Before entry, the organization received another chance to consider the same branch. Mars Climate Orbiter had been lost a little over 2 months before Polar Lander's arrival. In response, a special team reviewed Mars Polar Lander's readiness and built fault trees for possible failures during entry, descent, and landing. The eventual most probable cause appeared in that pre-entry analysis as a potential failure mode. That sentence can sound like a documented warning was knowingly ignored. The report does not support that conclusion. The software design and testing were described in a way that left the review team without concern. The branch was present. The implementation danger inside it was not understood. A fault tree can name what might go wrong without proving the controls against it are real. If the description says early events are ignored, the box can look closed even while the implementation preserves one. The hazard had been named without being exposed. The loss report did not treat this as one isolated coding mistake. It found no documented review plan and identified weaknesses in review formality, independent technical participation, action closure, and traceability. The board also said funding limitations probably affected the closure of actions. Those findings do not prove that any one review practice caused the final shutdown. They describe the safeguards around requirements, implementation, testing, and readiness. Mars Polar Lander's probable failure moved through boundaries between mechanical behavior, sensor input, software state, test configuration, and mission operations. Each boundary offered a chance to reveal the interaction, and a chance for one group to believe another layer had made it safe. The ruin mechanics reading is not that one transient destroyed a lander. It is that a transient became dangerous because the system accepted it, retained it, failed to test the complete path, reviewed an incomplete description of the protection, and flew without a live record of the result. The absence of live entry, descent, and landing telemetry was not an accident discovered after launch. The project had decided not to provide it under its cost and mission success criteria. Senior management at headquarters and the laboratory concurred. From the project's viewpoint, the loss board called that decision understandable. Telemetry adds mass, cost, power, complexity, and more things that must work. From the wider Mars program viewpoint, the board judged the omission unjustifiable. When the lander disappeared, the program received no performance record from the most dangerous part of the mission. The independent assessment team used stronger language. It called the lack of entry, descent, and landing data a major mistake because it prevented both reconstruction and learning for future missions. The mission did plan to collect engineering data during descent. The press kit said that data would be stored and included in the first transmission after landing. The design did not create no data. It made recovery of that data depend on the lander surviving and calling home. When the call never came, the probable cause and the evidence architecture became inseparable. Mars Polar Lander was developed inside a program with severe constraints. The loss board recorded a 15% mass margin at preliminary design review and described at least 25% as prudent for a new design. It said effort that could have reduced other risks went toward reducing mass. The independent assessment team argued that Mars 98 was underfunded by at least 30% after accounting for shared efficiencies. It described schedule, cost, science, and launch vehicle as fixed, leaving risk as the variable. Those are attributed program assessments. They do not prove a straight line from budget pressure to a shutdown command 40 meters above Mars. They describe the environment in which test coverage, review depth, independent participation, telemetry, margin, and closure competed for resources. Calling the loss simply faster, better, cheaper would replace a documented mechanism with a slogan. Calling it simply a software bug would erase how the program tested, reviewed, observed, and managed the system around it. Mars Polar Lander is lost. The most probable explanation is that leg deployment created a false touchdown indication, the software retained it, and enabling touchdown logic at about 40 meters shut down the engines. No flight record proves that sequence. 6 other failure modes remained possible. The 2 Deep Space 2 probes arriving with the lander were also lost, but the board could not identify their probable cause. Their silence cannot be assigned to Polar Lander's touchdown logic. The lesson is not never trust a sensor. The transient was known behavior. The real configuration never proved how hardware behavior, software memory, timing, and engine logic interacted. And when that proof failed on Earth, the mission carried no live evidence channel to settle the question at Mars. That is why NASA thinks the engines shut down 40 meters early, not because anyone watched it happen, but because one chain connected test evidence, code behavior, timing, and consequence better than the alternatives. Every collapse has a mechanism. Sometimes the last missing part is the mechanism that would have let you see it. As always, thanks for watching. If you enjoyed this video, feel free to subscribe. I'll see you in the next one.